Relativity, momentum, mass, energy, and gravity. Objectives. Describe how an object's momentum changes as it approaches the speed of light. Describe how mass and energy are related. Describe how the correspondence principle applies to special relativity. State the principle of equivalence. Describe the relationship between the presence of mass and the curvature of space-time. Describe Einstein's predictions based on his theory of general relativity. The big idea. According to special relativity, mass and energy are equivalent. According to general relativity, gravity causes space to become curved and time to undergo changes. No material object, particle, or future spaceship can be accelerated to the speed of light. Why this is so has to do with momentum and energy, which, in relativity theory, have new definitions. One of the most celebrated outcomes of special relativity is the discovery that mass and energy are one and the same thing, as described by E equals mc squared. Einstein's general theory of relativity, developed a decade after his special theory of relativity, offers another celebrated outcome, an alternate to Newton's theory of gravity. Both theories of relativity have changed the way we see the universe. How can space-time be modeled? Stretch a plastic garbage bag tightly across the top of a trash can. Tape the edges of the bag to the side of the can. Place a pool ball or other heavy sphere in the center of the garbage bag. This should cause the bag to sag in the center. Launch a marble by giving it a velocity tangent to the circumference of the can. 4. Try launching the marble with a variety of initial velocities. Discover, analyze, and conclude. 1. Observing. Describe the motion of the marble. What effect does changing the initial speed and direction of the marble have on the shape of the orbit? Predicting. How might changing the mass of the heavy center sphere affect the motion of the marble? Making generalizations. How closely does this model represent the motion of Earth's satellites? 16.1 Momentum and inertia in relativity. If we push an object that is free to move, it will accelerate. If we maintain a steady push, it will accelerate to higher and higher speeds. If we push with a greater and greater force, we expect the acceleration in turn to increase. It might seem that the speed should increase without limit, but there is a speed limit in the universe, the speed of light. In fact, we cannot accelerate any material object enough to reach the speed of light, let alone surpass it. At least one thing reaches the speed of light, light itself. But a particle of light has no rest mass. A material particle can never be brought to the speed of light. Light can never be brought to rest. Newtonian relativistic momentum. We can understand this from Newton's second law, which Newton originally expressed in terms of momentum, F equals mv over delta t, which reduces to the familiar F equals ma, or A equals F over m. The momentum form, interestingly, remains valid in relativity theory. Recall from chapter 8 that the change in momentum of an object is equal to the impulse applied to it. Apply more impulse and the object acquires more momentum. Double the impulse and the momentum doubles. Apply 10 times as much impulse and the object gains 10 times as much momentum. Does this mean that momentum can increase without any limit, even though speed cannot? Yes, it does. We learned that momentum equals mass times velocity. In equation forms, P equals mv, we use P for momentum. To Newton, infinite momentum would mean infinite speed. Not so in relativity. Einstein showed that a new definition of momentum is required. It is P equals mv divided by root 1 minus v squared over c squared, where v is the speed of an object and c is the speed of light. This is relativistic momentum, which is noticeable at speeds approaching the speed of light. So nothing that has mass can be pushed to the speed of light, much less beyond it. Hence, we can see that c is the speed limit in the universe. What if v is much less than c? Then the denominator of the equation is nearly equal to 1, and p is nearly equal to mv. Newton's definition of momentum is valid at low speed. Trajectory of high-speed particles. We often say that a particle pushed close to the speed of light acts as if its mass were increasing because its momentum, its inertia in motion, increases more than its speed increases. The rest mass of an object, represented by m in the equation on the previous page, is a true constant, a property of the object no matter what speed it has. Subatomic particles are routinely pushed to nearly the speed of light. The momenta of such particles may be thousands of times more than the Newton expression mv predicts. One way to look at the momentum of high-speed particles is in terms of the stiffness of its trajectory. The more momentum it has, the harder it is to deflect it. The stiffer is its trajectory. If it has a lot of momentum, it more greatly resists changing course. This can be seen when a beam of electrons is directed into a magnetic field, as shown in figure 16.1. Charged particles moving in a magnetic field experience a force that deflects them from their normal paths. For a particle with a small momentum, the path curves sharply. Figure 16.1. If the momentum of the electrons were equal to Newtonian values mv, the beam would follow the dashed line. But because the relativistic momentum or inertia in motion is greater, the beam follows the stiffer trajectory shown by the solid line. Notice that the square root in the denominator looks like the one in the formula for time dilation in chapter 15. It tells us that the relativistic momentum of an object of mass m and speed v is larger than mv by a factor of 1 over root 1 minus v squared over c squared. As an object approaches the speed of light, its momentum increases dramatically. As v approaches c, the denominator of the equation approaches 0. This means that the momentum approaches infinity. An object pushed to the speed of light would have momentum, infinite momentum, and would require an infinite pulse, which is clearly impossible. For a particle with a large momentum, the path curves only little. Its trajectory is stiffer. At ordinary speeds, an object's momentum is simply its classical value, mv. For example, at 30 meters per second, and that many zeros with 1, c, the relativistic momentum differs from the classical value by less than 1/trillionth of a percent. Newton's definition of momentum is valid at low speeds. Even though one particle may be moving only a little faster than another one, say 99.9% of the speed of light instead of 99% of the speed of light, its momentum will be considerably greater and it will follow a straighter path in the magnetic field. Through such experiments, physicists work with subatomic particles at atomic accelerators, verify every day the correctness of the relativistic definition of momentum and the speed limit imposed by nature. Concept check. How does an object's momentum change as it approaches the speed of light? 16.2 Equivalence of Mass and Energy. A remarkable insight of Einstein's special theory of relativity is his conclusion that mass is simply a form of energy, a piece of matter, even if at rest and even if not interacting with anything else, has an energy of being called its rest energy. Einstein concluded that it takes energy to make mass, and that energy is released when mass disappears. Rest mass is, in effect, a kind of potential energy. Mass stores energy, just as a boulder rolled to the top of a hill stores energy. When the mass of something decreases, as it can do in nuclear reactions, energy is released, just as the boulder rolling to the bottom of the hill releases energy. Conversion of mass to energy. The amount of rest energy, E, is related to the mass m by the most celebrated equation of the 20th century. E equals mc squared, where c is again the speed of light. This equation gives the total energy content of a piece of stationary matter of mass m. Mass and energy are equivalent. Anything with mass also has energy. In ordinary units of measurement, the speed of light c is a large quantity and its square is even larger. This means that a small amount of mass stores a large amount of energy. The quantity c squared is a conversion factor. It converts the measurement of mass to the measurement of equivalent energy. It is the ratio of rest energy to mass. E over m equals c squared. Its appearance in either form of this equation has nothing to do with light and nothing to do with motion. The magnitude of c squared is 90 quadrillion, or 10 to the 9 times 10 to the 16th joules per kilogram. 1 kilogram of matter has an energy of being equal to 90 quadrillion joules. Even a speck of matter with a mass of only 1 milligram has a rest energy of 90 billion joules. This is equivalent to the kinetic energy of 3-ton truck moving at over 20 times the speed of sound. Examples of mass energy conversions. Rest energy, like any form of energy, can be converted to other forms. When we strike a match, for example, a chemical reaction occurs and heat is released. Phosphorus atoms in the match had rearranged themselves and combined with oxygen in the air to form new molecules. The resulting molecules have very slightly less mass than the separate phosphorus and oxygen molecules. Think. Can we look at the equation E equals mc squared in another way and say that matter transforms into pure energy when it is traveling at the speed of light squared? No, no, no. Matter cannot be made to move at the speed of light, let alone the speed of light squared, which is not a speed. The equation E equals mc squared simply means that energy and mass are two sides of the same coin. From a mass standpoint, the whole is slightly less than the sum of its parts, but not by very much. By only about 1 part in billion for all chemical reactions that give off energy, there is a corresponding decrease in mass. In nuclear reactions, the decrease in rest mass is considerably more than in chemical reactions, about 1 part in 1,000. This decrease of mass in the sun by the process of thermonuclear fusion bathes the solar system with radiant energy and nourishes life. The sun is so massive that in 1,000,000 years, only 1/10,000,000th of the sun's rest mass will have been converted to radiant energy. Figure 16.2. In 1 second, 14.5 million tons of rest mass are converted to radiant energy in the sun. The present stage of thermonuclear fusion in the sun has been going on for the past 5 billion years, and there is sufficient hydrogen fuel for fusion to last another 5 billion years. It is nice to have such a big sun. Nuclear power plants, such as the one shown in figure 16.3, make use of the equivalence of mass and energy to produce enormous amounts of energy. The equation E equals mc squared is not restricted to chemical and nuclear reactions. A change in energy of any object at rest is accompanied by a change in its mass. The filament of a light bulb has more mass when it is energized with electricity than when it is turned off. A hot cup of tea has more mass than the same cup of tea when cold. A wound-up clock spring has more mass than the same clock when unwound. Figure 16.3, saying that a power station delivers 90 million megajoules of energy to its consumers is equivalent to saying that it delivers 1 gram of energy to its customers, because mass and energy are equivalent. But these examples involve incredibly small changes in mass, too small to be measured by conventional methods. No wonder the fundamental relationship between mass and energy was not discovered until the 1900s. The equation E equals mc squared is more than a formula for the conversion of rest mass into other kinds of energy, or vice versa. It states that energy and mass are the same thing. Mass is simply congealed energy. E equals mc squared says that mass is congealed energy. Mass and energy are two sides of the same coin. If you want to know how much energy is in a system, measure its mass. For an object at rest, its energy is its mass. Shake a massive object back and forth, it is energy itself that is hard to shake. Concept check. What is the relationship between mass and energy? 16.3. The Correspondence Principle. If a new theory is to be valid, it must account for the verified results of the old theory. The Correspondence Principle states that new theory and old must overlap and agree in the region where the results of the old theory have been fully verified. It was advanced as a principle by the Danish physicist Niels Bohr earlier in this century, when Newtonian mechanics was being challenged by both quantum theory and relativity. Notes: equations remind us that you can never change only one thing. Change a term on one side of an equation, and you change something on the other side. According to the correspondence principle, if the equations of special relativity or any other new theory are to be valid, they must correspond to those of Newtonian mechanics, classical mechanics, when speeds much less than the speed of light are considered. The relativity equations for time dilation, length contraction, and momentum are T equals T naught over root 1 minus v squared over c squared. L equals L naught times root 1 minus v squared over c squared. And P, the momentum, equals mv divided by root 1 minus v squared over c squared. We can see that each of these equations reduces to a Newtonian value for speeds that are very small compared with c. Then the ratio of v squared over c squared is very small, and for everyday speeds may be taken to be 0. The relativity equations become t equals t naught over root 1 minus 0, L equals L naught times root 1 minus 0, and P equals mv divided by root 1 minus 0. Remember, root 1 is simply 1. So, for everyday speeds, the time scales and length scales of moving objects are essentially unchanged. Also, the Newtonian equations for momentum hold true, and so does the Newtonian equation for kinetic energy. But when the speed of light is approached, things change dramatically. Near the speed of light, Newtonian mechanics change completely. The equations of special relativity hold for all speeds, although they are significant only for speeds near the speed of light. Notes: Much of nature is built on patterns, and looking for those patterns is the primary preoccupation of both artists and scientists. We connect things that were always there, but never put together in our thinking. So we see the advances in science take place not by discarding the current ideas and techniques, but by extending them to reveal new implications. Einstein never claimed that accepted laws of physics were wrong, but instead showed that the laws of physics implied something that hadn't before been appreciated. The special theory of relativity is about motion observed in uniformly moving frames of reference, which is why it is called special. Einstein's conviction that the laws of nature should be expressed in the same form in every frame of reference, accelerated as well as non-accelerated, was the primary motivation that led him to develop the general theory of relativity, a new theory of gravitation, in which gravity causes space to become curved and time to slow down. Concept check. How does the correspondence principle apply to special relativity? 16.4 General Relativity. Einstein was led to a new theory of gravity by thinking about observers in accelerated motion. He imagined himself in a spaceship far away from gravitational influences, as shown in figure 16.4. In such a spaceship, as at rest or in uniform motion relative to distant stars, Einstein and everything within the ship would float freely. There would be no up and no down. But if rocket motors were activated to accelerate the ship, things would be different. Phenomena similar to gravity would be observed. The wall adjacent to the rocket motors, the floor, would push up against occupants and give them the sensation of weight. Figure 16.4. Imagine being on a spaceship far away from gravitational influences. A. Everything inside is weightless when the spaceship isn't accelerating. B. When the spaceship accelerates, an occupant inside feels gravity. Einstein actually envisioned himself in elevators, not spaceships. If the acceleration of the ship were equal to g, the occupants could well be convinced the ship is not accelerating, but was at rest on the surface of Earth. The principle of equivalence. Einstein concluded in what is now called the principle of equivalence that gravity and accelerated motion through space-time are related. The principle of equivalence states that local observations made in an accelerated frame of reference cannot be distinguished from observations made in a Newtonian gravitational field. There is no way you can tell whether you are being pulled by gravity or being accelerated. The effects of gravity and the effects of acceleration are equivalent. To examine this new gravity in the accelerating spaceship, Einstein considered the consequence of dropping two balls, say one wood and the other lead. Figure 16.5 shows that when released, the balls would continue to move upward side by side with the velocity that the ship had at the moment of release. If the ship were moving at constant velocity, zero acceleration, the balls would appear to remain suspended in the same place, since both the ship and the balls move the same amount. To an observer inside the accelerating ship, a lead ball and a wood ball accelerated downward together when released, just as they would if pulled by gravity. But if the ship were accelerating, the floor would move upward faster than the balls, which would soon be intercepted by the floor. Both balls, regardless of their masses, would meet the floor at the same time. Occupants of the spaceship might attribute their observations to the force of gravity. Both interpretations of the falling balls are equally valid. Einstein incorporated this equivalence or impossibility of distinguishing between gravitation and acceleration in the foundation of his general theory of relativity. The principle of equivalence would be interesting but not revolutionary if it applied only to mechanical phenomena. But Einstein went further and stated that the principle holds for all natural phenomena, including optical, electromagnetic, and mechanical phenomena. Bending of light by gravity. Just as a tossed ball curves in a gravitational field, so does a light beam. Consider a ball thrown sideways in a stationary spaceship in the absence of gravity. The ball will follow a straight line path relative to both an observer inside the ship and to a stationary observer outside the spaceship. But if the ship is accelerating, the floor overtakes the ball and it hits the wall below the level at which it was thrown. An observer outside the ship still sees a straight line path as illustrated in figure 16.6a, but to an observer in the accelerating ship, the path is curved. It is a parabola as shown in figure 16.6b. Figure 16.7 illustrates that the same holds true for a light beam. A ball is thrown sideways in an accelerating spaceship in the absence of gravity. A. An outside observer sees the ball travel in a straight line. B. To an inside observer, the ball follows a parabolic path, as if in a gravitational field. A light ray enters the spaceship horizontally through a side window. A. Like the ball in figure 16.6, light appears to an outside observer to be traveling horizontally in a straight line. B. To an inside observer, the light appears to bend. The only difference is in the amount of path curvature, as shown in figure 16.8. If a ball were thrown at nearly the speed of light, the curvature of its path would be nearly the same as that of the light beam. Using his principle of equivalence, Einstein took another giant step that led him to the general theory of relativity. He reasoned that since acceleration, a space-time effect, can mimic gravity, a force, perhaps gravity is not a separate force after all. Perhaps it is nothing but a manifestation of space-time. From this bold idea, he derived the mathematics of gravity as being a result of curved space-time. 16.8. The trajectory of a baseball tossed at nearly the speed of light closely follows the trajectory of a beam of light. According to Newton, tossed balls curve because of a force of gravity. According to Einstein, tossed balls and light don't curve because of any force, but because the space-time in which they travel is curved. Concept check. What does the principle of equivalence state? 16.5. Gravity, space, and a new geometry. Space-time has 4 dimensions. 3 space dimensions, such as length, width, and height, and 1 time dimension, past to future. Einstein perceived a gravitational field as a geometric warping of 4-dimensional space-time. 4-dimensional geometry is altogether different from the 3-dimensional geometry introduced by Euclid centuries earlier. Euclidean geometry, the ordinary geometry taught in school, is no longer valid when applied to objects in the presence of strong gravitational fields. Think. Whoa! We learned previously that the pull of gravity is an interaction between masses, and we learned that light has no mass. Now we say that light can be bent by gravity. Isn't this a contradiction? There is no contradiction when the mass-energy equivalence is understood. It's true that light is massless, but it is not energyless. The fact that gravity deflects light is evidence that gravity pulls on the energy of light. Energy indeed is equivalent to mass. 4-dimensional geometry. The familiar rules of Euclidean geometry pertain to various figures that can be drawn on a flat surface. In Euclidean geometry, the ratio of the circumference of a circle to its diameter is equal to pi. All the angles in a triangle add up to 180 degrees, and the shortest distance between 2 points is a straight line. The rules of Euclidean geometry are valid in flat space, but if you draw circles or triangles on a curved surface like a sphere or a saddle-shaped object, as shown in figure 16.9, the Euclidean rules no longer hold. If you measure the sum of the angles for a triangle drawn on the outside of a ball, positive curvature, the sum of the angles is greater than 180 degrees. The sum of the angles of a triangle is not always 180 degrees. A. On a flat surface, the sum is 180 degrees. B. On a spherical surface, the sum is greater than 180 degrees. And on a saddle-shaped surface, the sum is less than 180 degrees. For a triangle drawn on a saddle, negative curvature, the sum is less than 180 degrees. Similarly, the geometry of Earth's 2-dimensional curved surface differs from the Euclidean geometry of a flat plane. As shown in figure 1610a, the sum of the angles for an equilateral triangle, the one here has the sides equal 1/4 Earth's circumference, is greater than 180 degrees. Earth's circumference is only twice its diameter, as illustrated in figure 1610b, instead of 3.14 times its diameter. Of course, the lines forming the triangles in figures 16.9 and 16.10 are not straight from the 3-dimensional view, but are the straightest or shortest distances between 2 points if we are confined to the curved surface. The geometry of Earth's two-dimensional curved surface differs from the Euclidean geometry of a flat plane. You have A and B. These lines of shortest distance are called geodesics. The path of a light beam follows a geodesic. Suppose 3 experiments on planets, Earth, Venus, and Mars, measure the angles of a triangle formed by light beams traveling between them. The light beams bend when passing the sun, resulting in the sum of the 3 angles being larger than 180 degrees, as illustrated in figure 16.11. So the 3-dimensional space around the sun is positively curved. The planets that orbit the sun travel along 4-dimensional geodesics in this positively curved space-time. Freely falling objects, satellites, and light rays all travel along geodesics in 4-dimensional space-time. Figure 16.11, the light rays joining the 3 planets form a triangle. Since the sun's gravity bends the light rays, the sum of the angles of the resulting triangle is greater than 180 degrees. The shape of the universe. Although space-time is curved locally within our solar system or within gravity, recent evidence shows that the universe as a whole is flat. This is a striking knife-edge condition. There are an infinite number of possible positive curvatures to space-time and an infinite number of possible negative curvatures, but only one condition of zero curvature. A universe of zero or negative curvature is open-ended and extends without limits. If the universe had positive curvature, it would close in on itself, just as the surface of Earth closes in on itself. If you march straight ahead on Earth, never turning, you eventually return to the starting point. And if you shine a flashlight into space of positive curvature, the light will eventually illuminate the back of your head if you wait long enough. No one knows why the universe is actually flat or nearly flat. The leading theory is that this is the result of an incredibly large and near instantaneous inflation that took place as part of the Big Bang some 13.7 billion years ago. General relativity, then, calls for a new geometry, a geometry not only of curved space, but of curved time as well, a geometry of curved 4-dimensional space-time. Even if the universe at large has no average curvature, there's very much curvature near massive bodies. The presence of mass produces a curvature of warping of space-time. Conversely, a curvature of space-time reveals the presence of mass. Instead of visualizing gravitational force between masses, we abandon altogether the idea of force and think of masses responding in their motion to the curvature or warping of the space-time they inhabit. General relativity tells us that the bumps, depressions, and warpings of geometrical space-time are gravity. We cannot visualize the 4-dimensional bumps and depressions in space-time because we are 3-dimensional beings. Look at an airplane's flight path drawn on a flat map, and you'll see that the line is curved. The same line drawn on the surface of a globe would be a geodesic, a straight, shortest possible distance between 2 points, line on Earth's curved surface. We can get a glimpse of this warping by considering a simplified analogy in 2 dimensions. A heavy ball resting on the middle of a waterbed, which is illustrated in figure 1612. Figure 1612, space-time near a star is curved in a way similar to the surface of a waterbed when a heavy ball rests on it. The more massive the ball, the more it dents or warps the two-dimensional surface. A marble rolling across such a surface may trace an oval curve and orbit the ball. The planets that orbit the Sun similarly travel along a four-dimensional geodesics in the warped space-time about the Sun. Gravitational waves. Every object has mass, and therefore makes a bump or depression in the surrounding space-time. When an object moves, the surrounding warp of space and time moves to readjust to the new position. These readjustments produce ripples in the overall geometry of space-time, similar to moving a ball that rests on the surface of a waterbed. A disturbance ripples across the waterbed surface in waves. If we move a more massive ball, then we get a greater disturbance and the production of even stronger waves. The ripples that travel outward from the gravitational source at the speed of light are gravitational waves. Any accelerating object produces a gravitational wave. In general, the more massive the object and greater its acceleration, the stronger the resulting gravitational wave. But even the strongest waves produced by ordinary astronomical events are the weakest known in nature. For example, the gravitational waves emitted by a vibrating electric charge are a trillion times weaker than the electromagnetic waves emitted by the same charge. Detecting gravitational waves is enormously difficult, but physicists think they may be able to do it, and searches are underway at present. Concept check. What is the relationship between the presence of mass and the curvature of space-time? 16.6. Tests of general relativity. Upon developing the general theory of relativity, Einstein predicted that the elliptical orbits of the planets precess about the Sun. Starlight passing close to the Sun is deflected, and gravitational causes time to slow down. Later, his predictions were successfully tested and confirmed. Precession of the planetary orbits. Using four-dimensional field equations, Einstein recalculated the orbits of the planets about the Sun. Planets and comets travel along curved paths because of the curvature of space-time. With only one minor exception, his theory gave almost exactly the same results as Newton's law of gravity. The exception was that Einstein's theory predicted that the elliptical orbits of the planets should precess independent of the Newtonian influence of other planets, as shown in figure 1613. This precession would be very slight for distant planets and more pronounced close to the Sun. Mercury is the only planet close enough to the Sun for the curvature of space to produce an effect big enough to measure. Precession in the orbits of planets caused by perturbations of other planets was well known. Since the early 1800s, astronomers measured a precession of Mercury's orbit, about 574 seconds of arc per century. Figure 1613, Einstein's theory predicted that elliptical orbits of the planets should precess. Perturbations by the other planets were found to account for the precession, except for 43 seconds of arc per century. Even after all known corrections due to possible perturbations by other planets had been applied, the calculations of scientists failed to account for the extra 43 seconds of arc. Either Venus was extra massive or a never discovered other planet called Vulcan was pulling on Mercury. And then came the explanation of Einstein, whose general relativity equation applied to Mercury's orbit predict the extra 43 seconds of arc per century. Deflection of starlight. As a second test of his theory, Einstein predicted that starlight passing close to the sun would be deflected by an angle of 1.75 seconds of arc, large enough to be measured. This deflection of starlight can be observed during an eclipse of the sun. Measuring this deflection has become a standard practice at every total eclipse since the first measurements were made during the total eclipse of 1919. A photograph taken of the darkened sky around the eclipsed sun reveals the presence of the nearby bright stars. The positions of the stars are compared with those in other photographs of the same part of the sky taken at night with the same telescope. Think, why do we not notice the bending of light by gravity in our everyday environment? Earth's gravity is too weak to produce a measurable bending. Even the sun produces only a tiny deflection. It takes a whole galaxy to bend light appreciably. In every instance, the deflection of starlight, which is illustrated in figure 1614, has supported Einstein's prediction. More support is provided by gravitational lensing, a phenomena in which light from a distant galaxy is bent as it passes by a nearer galaxy in such a way that multiple images of the distant galaxy appear. Gravitational redshift. Einstein made a third prediction, that gravity causes clocks to run slow. He predicted that clocks on the first floor of a building should tick slightly more slowly than clocks on the top floor, which are farther from Earth and at a higher gravitation potential energy. Figure 1614, starlight bends as it grazes the sun. Point A shows the apparent position. Point B shows the true position. The deflection is exaggerated. As shown in figure 1615, if you move from a distant point down to the surface of Earth, you move in the direction that the gravitational force acts toward lower potential energy, where clocks run more slowly. From the top to the bottom of the tallest skyscraper, the difference is very small, only a few millionths of a second per decade, because the difference in Earth's gravitation at the bottom and top of the skyscraper is very small. For larger differences, like those at the surface of the sun compared with the surface of Earth, the clock slowing effect is more pronounced. A clock in the deeper potential well at the surface of the sun should run measurably slower than a clock at the surface of Earth. 1615, gravity causes clocks to run slow. A clock at the surface of Earth runs slower than a clock farther away. Einstein suggested a way to measure this. Light traveling against gravity is observed to have a slightly lower frequency due to an effect called the gravitational redshift, because red light is at the low frequency end of the visible spectrum. A lowering of frequency shifts the color of the emitted light towards the red. Although this effect is weak in the gravitational field of the sun, It is stronger in more compact stars with greater surface gravity. An experiment confirming Einstein's prediction was performed in 1960 with high-frequency gamma rays sent between the top and bottom floors of a laboratory building at Harvard University. Incredibly precise measurements confirmed the gravitational slowing of time. So measurements of time depend not only on relative motion, as we learned in special relativity, but also on gravity. In special relativity, time dilation depends on the speed of one frame of reference relative to another. In general relativity, the gravitational redshift depends on the location of one point in the gravitational field relative to another one. It is important to note the relativistic nature of time in both special relativity and general relativity. Notes: the medieval philosopher William of Ockham said that when deciding between two competing theories, choose the simpler explanation. Don't make more assumptions than are necessary when describing phenomena. In both theories, however, there is no way that you can extend the duration of your own experience. Others moving at different speeds or in different gravitational fields may see you aging slowly, but your aging is seen from their frame of reference, never your own. As mentioned earlier, changes in time and other relativistic effects are always attributed to the other guy. Concept check. What three predictions did Einstein make based on his general theory of relativity? Newton's and Einstein's gravity compared, connection to space science. From Newton's law, one can calculate the orbits of comets and asteroids and even predict the existence of undiscovered planets. Even today, when computing the trajectories of space probes throughout the solar system and beyond, only ordinary Newtonian theory is used. This is because the gravitational fields of these bodies are very weak, and from the viewpoint of general relativity, the surrounding space-time is essentially flat. But for regions of more intense gravitation, where space-time is more appreciably curved, Newtonian theory cannot adequately account for various phenomena, like the precession of Mercury's orbit close to the Sun, and, in the case of stronger fields, the gravitational redshift and other apparent distortions of space and time. These distortions reach their limit in the case of a star that collapses to a black hole, where space-time completely folds over on itself. Only Einsteinian gravitation reaches into this domain. Summary: relativity, momentum, mass, energy, and gravity. As an object approaches the speed of light, its momentum increases dramatically. Mass and energy are equivalent. Anything with mass also has energy. According to the correspondence principle, if the equations of special relativity or any other new theory are to be valid, they must correspond to those of Newtonian mechanics, when speeds much less than the speed of light are considered. The principle of equivalence states that local observations made in the accelerated frame of reference cannot be distinguished from observations made in a Newtonian gravitational field. The presence of mass produces a curvature or warping of space-time. Conversely, a curvature of space-time reveals the presence of mass. Upon developing the general theory of relativity, Einstein predicted that the elliptical orbits of the planets precess about the Sun. Starlight passing close to the Sun is deflected, and gravitation causes time to slow down.